So Vaidehi,
Yes.
so should we wait a couple of minutes or so?
Yeah. I think we should wait for like 1 or 2 minutes for others to join.
Okay.
Yeah. Hello everyone. I hope you can hear me well, and I guess now we can start. We are already 2 minutes past the hour. So, welcome to the seminar, uh, which we are trying to conduct on a weekly basis. So, before we start, I request everyone that we have, as discussed with the director, that the plan is to organize this astrophysics seminar every week on Tuesday on this regular timing. So, if you have any new result, your paper gets accepted, or if you are aware of any potential speakers, so please do let the colloquium committee know, and we will be more than happy to schedule the seminar based on the mutually agreeable date. So we can start. Today's talk will be by Indranil, and he will talk about his work, which was recently published on simulation of radiation-driven winds from Keplerian disks. So Indranil, please go ahead when you're ready.
Okay. Thank you. Am I audible?
Yes, we can hear you well.
Okay, fine. So thank you for this opportunity to speak. There's a mistake here. I should have added the two people who are also part of this work. One is my ex-student Mukesh, and the other is Sananda. He worked with me. I'm not a formal guide, but sort of she worked with me in her PhD, and this work will go into her thesis as well. Anyway, so so we'll be talking about radiation-driven winds from Keplerian disks. Okay, hang on, what happened? Just a minute, something's wrong. Can you hear me?
Yes, we can hear you, and we can see you the first slide, title slide we can see.
Yeah, but I don't know why something is stuck. Just a minute. Okay. All right. So I think now I can whatever. Yeah. So is it working? Yeah, it's working now. For some reason it got stuck. I don't know why. So anyway, so I'll be talking about simulations of radiation-driven winds from Keplerian disks. So I will sort of give a basic definition of winds, jets, and a broad observational, definitions, and then I'll pose the problem. Then I'll discuss about the results and conclusions, so on. So just, this black hole image, a couple of years old, no more the new kid in the town, but anyway, it's the most novel thing we have at the moment. Anyway, so what are AGNs? So if you go by the definition, AGN is essentially the effect of a supermassive black hole at the center of galaxy has on the galaxy. Okay, as the effect, whatever activity we can think about is because of the central black hole sitting there and pulling matter and throwing some part of the pulled up matter and so on. So that is basically the activity. So here we have this central black hole, and there is the whole galaxy to feed it. And there are many examples of various galaxies and the centers of which we generally have a black hole. I mean, initially people thought that there will be galaxies which will not have a central black hole, but it looks like most galaxies, if not all galaxies, have a central black hole. And what are microquasars? As you can understand from the very word micro, it's a small quasar. That means it mimics a quasar or an AGN in a smaller scale. So it's essentially a central black hole or a neutron star and accompanied by a secondary star, a normal secondary star, main sequence secondary star. So, it's a cartoon diagram. You have this main sequence star, and there is this compact object somewhere there, and it strips of matter, and it creates this so-called accretion disk, and you can see some jets coming out and so on. Okay, so that's the definition of a microquasar and AGN. So the similarities between AGN and microquasar are that the luminosities are high, and high, of course, they are scalable with the mass of the central object. But the AGNs, it is very high. It's 10 to the 42 to 47 arcs per second, the luminosity. While for microquasars, it can be from 10 to the raise 37, 38 to close to 40, depending on which spectral state the microquasar is in. And it is scalable. That means whatever the central mass is, the luminosities tend to scale with that mass. So because AGNs have a higher mass, they have a higher luminosity, and microquasars have a lower mass and lower luminosity. Then the high energy emission is with significant non-thermal component, both in microquasars and AGNs. Although AGNs are much more broadband, microquasars are not really broadband. It is in the higher energy range, especially in the X-rays. I mean, there's a lot of emission in the X-rays. So it is, one can say microquasars are X-ray luminous, while AGNs are luminous in all wavelengths. And AGNs, some of the AGNs have relativistic jets, some don't. And microquasars also, they have relativistic jets in phases. Okay. So the differences, so that's the similarity we talked about. And what are the differences? The difference is the absolute length scale. AGNs are really huge, big, very big, while microquasars are smaller. And so it would be like, typically it would be like, if you can look at here, it will be that a microquasar would be an accretion disk, and so the length scales will be something like this, which will accompany an accretion disk and the accompanying star. So whatever that length scale might be, it's much smaller. And apart from short-term variabilities, and there are no straight transition in AGNs. Okay, I have to put some AGN word here. While microquasars are known to undergo state transition in a matter of months. Okay, so basically, once you see an AGN or a quasar, you sort of give it a type or a kind of AGN. It would be like, whether it's a FR1 or it's FR2. We don't see that FR1 goes to FR2. Okay, while microquasars always, goes from one state to another. Okay. However, although we have listed some differences, all these differences are scalable by mass. A typical accretion disk length scale is typically 10 to the power 5 or 6 Schwarzschild radius, okay, or gravitational radius. Okay, so that's the length scale. Okay, and the size of a black hole is its Schwarzschild radius or gravitational radius, and it turns out to be, it scales with the mass of the black hole. So it's like 3 kilometers into mass of the black hole by the mass of the sun. So this factor is dimensionless, and depending on what kind of mass you have, the definition or the actual length scale of the size of the black hole or the Schwarzschild radii will change. And so light crossing time would be like L by C, C being the speed of light, and it will be typically on 10 to 100 MB by M sun second. Okay, so if it's a microquasar, then if you plug in 10 solar mass, then this turns out to be 10 to the power 1 to 10 to the power 2 to 10 to the power 3. Okay, while so if you assume that there is some perturbation that is starting from the edge of the accretion disk and goes right up to the central object with, say, an average speed. Okay, this speed might vary, it might be much lower than what I have just quoted. So therefore, it's less than, on average speed, less than 1,000th of the speed of light. Okay, that implies that one can expect to see a state transition days to months time scale for a microquasar. The same thing will take about hundreds of years or 1,000 years, of course, depending on the mass of the black hole, for an AGN. Okay, so that's why in AGN we don't see a state transition, but in microquasars we see it in matter of months. Okay, all right. So therefore, that's what we wrote, that the AGN seems to hold its type. Some are jet spewing, some are not, while microquasars makes transition regularly. So while AGN, if you have to study AGNs to understand the entire universe and how it works and how the metallicity changes and so on, but if you want to also understand how, what are the timing properties of AGN, one has to keep microquasars in mind, and therefore people working in AGNs should know what microquasar people are doing, and what people working in microquasars should also take leaf out of AGNs. Okay, so black hole astrophysics was born with the discovery of this quasar 3C273 by Martin Schmidt long time back, and we all know that the tremendous luminosity that's stated at 45 arcs for this particular case. The tremendous luminosity that has been computed or estimated from this object cannot be produced by nucleosynthesis alone. One has to have to convert the matter falling into a very compact object and convert that into radiation. So that's a more efficient way of doing it rather than normal nucleosynthesis. Okay, so it's very efficient if provided that it is very compact. The energy released will be of the order of the rest mass energy of the matter falling in. So that this led to a frenetic search on what is the mode in which matter falls into a black hole. Okay, and by 1973, a community already knew that accretion has to have some rotation, because matter, if it's madly falling in, they don't have enough time to produce that much luminosity. Okay, there are many accretion disk models that came up, and one of them being what was proposed by Sakurai and Tsunaev, which is called the Keplerian accretion disk. Okay. Now, one of a few of the broad observational features that we see in microquasars, and that should also be reflected in AGNs. But while in AGNs you cannot see a straight transition, but you have to rather look at all kinds of AGNs and sort of do an ensemble search to find out these states. And there are few works at the moment where the low luminosity AGNs are being compared with what is called the hard state of microquasar. So what is a hard state? In the hard, if you look at the continuum spectra, so this is Cygnus X1, and you can see the continuum spectra is mostly in the X-rays, from soft X-rays to hard X-rays, but it's mostly in the X-rays. And we call it a hard state when there is a dominant power law or non-thermal contribution. Okay, and the power maximizes at high hard X-rays. Okay, so it's around 100 keV, the power is maximizing. Okay, and then you have a softer bump in case of Cygnus X1. In many other microquasars, you don't see it simultaneously with the hard in the hard state. So this is essentially a thermal bump, and it's supposed to come from the Keplerian disk. So basically, I'll discuss this later on. So it's basically an optically thick medium which is generating this thermal bump, and this is due to Comptonization or inverse Comptonization of the seed photons from this by hot electrons. Okay, and there is also something called the soft state. Okay, so this is Cygnus X1 hard state, and then there's a soft state. And these are all actual observations. And you can see in the soft state, it is dominated by this thermal bump, okay, which is supposed to come from the Keplerian disk. And then you have a weak power law. Okay, now what was a strong power law, then now we have weak power law. And also the power peaks at a lower energy. So that's why it's called soft state, in the soft side of the spectrum. Of course, the luminosity is higher, so it's called high soft state. And while when it is hard, the luminosity is lower, and therefore it is called low hard state. Okay, all right. And in the soft hard state, if you do a power density spectrum of this hard photons, this non-thermal photons, then the power density spectrum gives rise to some sort of a QPO. You can see there is a fundamental, and then there's a few harmonics. This is observation from GX3394. It's a black hole source, and we did something some time back, and we could sort of match the various harmonics of GX33914 by some sort of oscillation in the disk. But that's a different issue. We're not discussing that. So the broad features are that we have a hard state and we have a soft state. In the hard state, we have these power. I mean, if you sort of do a power density spectrum of the hard photons, non-thermal photons, it gives some quasi-periodic oscillation of this. So therefore, the part of the disk which is giving rise to these hard photons are also giving in a quasi-periodic oscillation. Okay, all right. And at the same time, these jets. Somehow this is a I think 3C. I forgot the name of this object. Okay, forgetting it anyway. So there are AGNs which are associated with relativistic jets. This is a Chandra observation, and like quasars, in the extra binaries or microquasars, we also see relativistic jets. This is a Nature paper a long time back, 1999, multi-wavelength observations in X-rays, in infrared, and in radio, where it was shown that when the X-ray dips, then you can see some radioactivity, and then after this spike, there is a relativistic ejection. Okay, so this is a Nature paper, and it was so when the X-ray dips, you see there's a hardness ratio here. It jumps up, and after the relativistic ejection, it goes down again. The hardness ratio goes down, but the X-rays again starts to increase. Okay, so and later in by Fender and Belloni, they studied a lot of microquasars and came up with an average description of the state transition of microquasars. So this is a hardness intensity diagram. It's intensity in this direction and the hardness ratio in that direction. And so when the microquasars in this low hard state, so you see the hardness ratio is high, but the luminosity is low, then you start to see some jet activity. So that there's some radioactivity, compact radio jets are coming out. It can be detected if there's simultaneous observations. And then after some time, the luminosity, keeping it is in the hard state, the luminosity starts to increase, and the jets also starts to become stronger. In other words, the radio, the compact radio emissions that are detected from these objects also starts to become very strong. And then so if it is in this state, between hard and soft, it is called the intermediate state. And then from the hard intermediate, when it jumps into soft intermediate, then there is a relativistic ejection, as it's seen in the left-hand side of this Q diagram. It's called this hardness intensity diagram. And once this relativistic ejections relativistic plasma is ejected, then it comes down to what is called the soft state, high soft state, which is at that time there are no radioactivities at all. Okay, so that this is what you can say that the average description of the state change in microquasars. Okay, now in radioquiet AGNs, as well as for X-ray binaries, which are in the soft state, there have been blue shifted absorption lines observed, okay, which can be interpreted as propagating winds. Okay, what is a wind? Wind is also an outflow, but it's an uncollimated outflow. It's sort of going in a large angle. Okay, while what is a jet? It's also outflow, but it's faster than a wind, and is collimated. Okay, so that's the difference between a jet and a jet outflow and a wind outflow. Okay, so now we see both the winds and the jet in AGNs as well as in microquasars. The difference is, I've taken it from Bianchi's one of the presentation. I was looking for this plot, but I could not find it, so I just stole it from his presentation. So what we see here in the soft state, forget about this second bump. Okay, this can be explained in different ways. Forget about that. We have this disk emission. Okay, so this you can see this is the disk emission. In black means it's a hard state, and the red is the soft state. So in the soft state, you can see that, as we saw in the previous case, that it doesn't extend very, there's a weak power law, but it's mostly dominated by multicolored black body or thermal emission. While in the hard state, we have this disk emission as well as a stronger non-thermal emission. But as we just discussed, the emissions from a compact jet is not there in the soft state, but it is there in the hard state. At the same time, we don't see that absorption features, which can be interpreted as a if not spherical, but is a wide angle wind that is coming out in the hard state, but in the soft state. Okay, the hard state we don't see it, but in the soft state we do see it. That absorption feature. If we summarize, then we can say that in the soft state we don't have a jet, but we have a wind, and in the hard state we don't have a wind, we have a jet. Okay, all right, and because both of them depend on the accretion disk state, therefore one can say that it is the same accretion phenomena, which is once giving out a broad wind, which is slower, and which is wide angle and it's spreading all over wind, and at some other state it is a relativistic, fast, and collimated outflow. Okay, so that's the, what should I say, is one can summarize from the observations. All right. Now, winds and agents are colder. That's number one. Number two is that since it is the winds are, in this talk we are only discussing about the winds. So in the soft state, because it's a wind, and in the soft state it is luminous, while it is giving rise, I mean, the radiation is dominated by a thermal radiation, which is associated with the Keplerian disk, something like this here. Okay, then we can probe that whether the top half of this disks, okay, can be ejected by the disk radiation itself or not. We can sort of probe that avenue. Okay, now winds and agents are colder, therefore may retain an atomic structure. So there are a lot of people who work on line driven mechanism. Okay, so what is a line driven mechanism? So if you have some outflow at the top of the disk, something like this, you have some matter here which retains, which is colder, therefore retains the atomic structure, and the radiation is coming from below. Okay, and then you have one atomic structure, like it might be partially ionized, that's always okay, but because it's colder, it has some electron around the nucleus, whatever that nucleus might be, and then there's a radiation that comes and hits it, such that the radiation, the energy of the radiation is matches with the ground state to the first excited state or second excited state energy gap between of the electron. So it goes from ground state to in the right hand side is the excited state. So with the bigger circle, I've sort of described it. So once this photon goes and hits an atom, so in the forward direction, not only it will give some energy, it will also give some momentum. Okay. After around 10 to the power minus 8 seconds, it will come back to its ground state. But then this, when it comes back to the ground state and gives out the photon, if you take the average out, the photons will be emitted in all directions isotropically. So there will be, when it is during the absorption, it is getting a forward momentum push, but when it is coming down in the ground state, the net momentum while it's coming down will be isotropic, and there will be no backward push. So by this method, it's called line locking or line driven mechanism, there can be a forward push, okay, of material above a cold disk or a cold material. Okay. However, around microquasars, what we showed, right, so lots and lots of X-rays, and therefore very unlikely that matter around microquasars will retain the atomic structure at all. So they will it will be fully ionized plasma, and then this line driven mechanism will not work. So what we studied is only electron photon interaction, Thomson scattering. Okay, so it's basically not Thomson scattering, but we're taking the Thomson scattering cross section, but it's basically quantization. Okay, so direct electron scattering of top portion of the disk matter by the disk radiation as a driving mechanism in the soft state of the accretion disk. Again, in the soft state, the disk is basically Keplerian disk. So what is a Keplerian disk? Keplerian disk has very low, almost negligible radial inflow, but it is rotating it is rotating with almost the Keplerian velocity. Keplerian velocity is the velocity that you get by matching the centrifugal force with the gravitational force. Okay, and it is optically thick because VR is very low. Therefore, matter actually stays in a certain orbit for a very long time. So it's optically thick, but it is geometrically thin. Because it's optically thick, it is radiation, the cooling dominated. Therefore, it will be geometrically thin. It will occupy the position around the equatorial plane, and its inner edge should be the ISCO. ISCO is the inner stable circular orbit, the last stable circular orbit. Okay, and the Keplerian velocity is given by this expression, and this continuum spectra is also of the disk is multicolored black body. Okay, all right. The equations of motions are these. These are time-dependent equation of motion in all fractions. What we have done is we have calculated what should be the radiation force in the radial direction, in the azimuthal direction, as well as in the z direction. Okay, and the fifth equation is the equation of the energy equation. All right, where this curly E is basically sum of the kinetic energy and the internal energy of the gas. And the internal energy of the gas is P by gamma minus 1, gamma being the specific heat, and the ratios of the specific heat, and its gamma is 5/3 because it's non-relativistic anyway. All right, and the small f, g, z, and g, r, these are all the radial component of the gravitational force and the z component or the z component of the gravitational force. Because it's spherical symmetric, so therefore there are no the phi component of the gravitational force. Okay, and these fr, this curly fr, f phi, and fz, these are all the radial component and the phi component, the z component of the radiation force. Okay, so that's Fi is here. So this is the flux, this is the energy density, and this is the various components of pressure. Okay, so this is RR, R phi. It's IR and I phi and IZ. Now you can change I from R theta, R phi and Z. All right, so this I is here. Okay, so that's what I say, various moments of the radiation field, and which basically the radiation energy density, fluxes, and various components of the radiation pressure. And these are, as I said, the components of the gravitational force. And the disk, this is the disk density, which can be calculated for a Keplerian disk. This is the radial component of the Keplerian disk. Okay, the radial component we can estimate. So we have one radius which is moving with, at one radius the matter is moving with some Keplerian angular, azimuthal velocity, and in the next radius it is moving with another velocity, and the viscous time scale will determine how long it will take from one radius to for a matter from one radius to come to the next radius, and from there we can estimate this VRK, the radial component of the Keplerian disk, and below we also have the temperature distribution of the Keplerian disk. Okay, and this is how we calculated the moments, the various moments. So at this point, say this is the axis, and this is the equatorial plane, and this is the surface of the disk. From there, radiation is coming at this point B. Say so. This is the disk point, source point, and this is the field. B is the field point, and so we take of the solid angle that B imposes on the point D, and then we integrate over to get the energy density. You take various components of how much energy is coming, they will give us flux. Okay, now if you take two components at the same time and you integrate, what you get is the pressure. Okay, all right, so that's what we did. Now, not only the matter is falling in, the matter is mostly rotating, right? So if it is rotating, the radiation that is being ejected will also have F5. I mean, sorry, a V5, or it will inject a phi component of the velocity. Okay, so it will so all the radiation will be emitted with the angular momentum, local angular momentum of the disk. Okay, of course, the total speed of the radiation will always be speed of light. So the net speed rather, but when it is rejected from a rotating matter, it will also have a lot of F phi, or the phi component of its velocity. Okay, so with all these things we integrate and find out what are the distribution of the moments, the radiation field movement. So in the panel A we have the energy density. Panel B, it is the radial flux. Okay, panel C is the phi flux, or the azimuthal, the flux, radiation flux along the azimuthal direction, and phi D is along the Z direction. Then panel E is PRR, the RR component of the radiation pressure. Then you have R phi, RZ, and then we have phi phi, then phi Z and ZZ. Okay, so all these independent components of the moments we calculate and we plug it in the equation of motion. Okay, and then we in a numerical simulation code we solve this equation. So the numerical, so the setup, the computational setup is something like this. On the left hand side we have the axis. So we put a reflective boundary condition. That means there is no azimuthal velocity, or the phi velocity on the axis. The phi velocity goes to 0 there, and while in the outer boundaries here and there we impose the outflow boundary condition, and we impose the Keplerian disk condition at the bottom. Okay, and then we simulate. All right. Okay, so this is a typical wind. So here is this greenish part is the accretion disk, and the radiation is here. All these radiation field is, so you have E, FR, FI, FZ, PRR, everything is being computed on this computational domain. And here you can see that matter is being ejected. Okay, and it's coming from a region less than 30 Schwarzschild radius. Okay, and so it is being ejected, and now you can see it is also being spread. A part of the matter which has been ejected also comes back and sort of comes back into the accretion disk itself. And you can see that there is a kind of a small vortex kind of a thing that is going on here. And what it does, it goes and hits the base of the wind. and as a result, it starts to sort of oscillate. A portion of it oscillates. All right. Okay. Now here we have plotted the V phi at a height of 6 Schwarzschild radius. Here at various time steps, it is written 30, 50, 60. The unit of time I think is 0.05 seconds. So if you put whatever computational setup we have given, turns out that the unit of time comes out to be 0.05 seconds. All right, and this is the Keplerian disk rotational velocity, and this is the rotational velocity of the wind at around 6 Schwarzschild radius above the disk. Okay. So now if we, so that's in one height, but if we look at the contour of the V phi, so this is the contour of the V phi for two different accretion rate. The radiation field is coming from the accretion disk below, and the matter supply gives the energy for the disk to radiate. Okay, so this is for one radiation accretion rate. This is for another accretion rate. All right. So here, what we have plotted is the effect of the radiation drag. Okay, what is radiation drag? If you look at the equations of motion, okay, so if you look at the radiation component, this Fr, Fi, and Fz, which is Fi here. So you have a plus term here, which is the flux, but then you have combination of energy density and velocities, okay, and the pressure and the velocity components. They come with the minus sign. So this is a decelerating term, while F, or the flux, is the accelerating term. So what happens is that if you look at this, the radiation from here, so above the disk, it is optically thin medium, right? So the radiation penetrates. So as this matter is trying to flow through it, so it sees the radiation field in front, okay, and they are blue shifted towards it, all right? And that gives a pressure, a sort of a radiation pressure, or it sort of holds back. It's something like if you throw a stone in air, the air in front of the stone, it drags it, okay, it sort of tries to hold it back. So radiation does the same, and we call it drag because it's also these terms, these deceleration terms, depends on the velocity. The faster it moves, the radiation drag will become larger. Okay, all right. So it is a kind of a what should I say? It's kind of a control mechanism so that things don't move very fast. And what we have done here, it's for various accretion rates. So the first two panels is for one accretion rate, the second is another, and third is another. So it's written here. Okay. And what we show here is that the importance of radiation drag terms. On the right hand side, we put the radiation drag terms equals to 0 in the code, and we run the code. And in the left hand side, we put all the terms and we run the code. What we see here for this particular accretion rate, if the radiation drag is actually holding it back, okay, it's not allowing the matter that has been ejected to actually leave the computational domain. While if you don't take the radiation drag term, it happily moves out. Okay, and because of this radiation drag term, we also see that there is this matter that is coming back and hitting the base is actually wiggling the column of the wind. Okay, and as we increase the radiation, sort of we make it move faster and faster. All right. Okay, so radiation drag. So here we have plotted for various accretion rate. We have plotted the terminal speed of the wind. Okay, by terminal speed, what we mean is the speed at which, after this matter goes and reaches the top half of the computational domain, what is the velocity here? Okay, that's we are calling it to be terminal speed. Okay, so what we see here is that without radiation drag, the speed, the terminal speed is very high. It's units of speed of light, so it's more than 10% the speed of light here. While if we have radiation drag, it limits the speed to much lower values. Okay. Not only that, if you calculate what is the mass outflow rate, okay. So if here we have just plotted the mass outflow rate for various accretion rates. So if you increase the radiation, then the mass outflow rate increases. Okay, but here what we have plotted is so it's the same thing here, but now this is along the radius, and here we have sort of plotted it along the Z boundary. Okay, so one is with the R boundary, the other is Z boundary. Now it's a total mass outflow rate, and without the radiation drag, we can see it's pretty high, while without the radiation drag term, it is much lower. All right, so the radiation drag terms, none of this, I mean, many people have did simulation of radiation driven winds, none of them taken this radiation drag term. So what we show here is that it's very important. It sort of limits to very much lower values than what you get without the radiation drag term. All right, so it is the so what we have plotted here is the percentage of the matter that is leaving the disk. What percentage of it is transonic or is crossing the sonic point? So you remember, in case of a particle, when we throw a particle up, it comes down. Why? Because we say that it doesn't have the escape speed. Okay. Now, for fluids, that's not the case. You don't need escape speed to get out of a gravitational field. What you need, what is called, whether it's transonic or not, because for a particle, you only have a kinetic speed to counter the gravity. But for a fluid, you have the kinetic term as well as the thermal term, which it also drives. So you can throw out a matter, a fluid, out of a gravitational field with starting speeds much lower than the escape speed. The only thing is that the kinetic term plus the thermal term has to negate the gravitational term. Okay. So what percentage of that matter that has been ejected is transonic? So here, for a higher accretion rate, we see that it is coming out to be 7%. Okay, this is with time. So at say after 70 into the unit of time, which is 0.05 seconds, about 70% of it is transonic, and here it is less than 6% all the time. Okay. All right. So here is the simulation of the case I just said, that it's in this particular case where the matter is being ejected, but because of the radiation drag, okay, the outflow has been suppressed. Okay. All right. So this is the density contour. This is the Z axis, and this is the R axis, and the disk is somewhere here. Okay, and some amount of matter is falling and settling over the accretion disk, and this is how it is it is getting quenched. Okay, and here it's a stronger radiation field, and you can see that matter is going out, but because some amount of matter is coming back and hitting the base, you can see there's a wiggling. It's almost like a garden hose instability, but one has to study this a little bit more. So the conclusions are radiations can drive winds in the electron scattering regime, and winds originate from regions closer to the center of the hole, and the radiation drag is very important. It limits the terminal speed as well as the total mass loss. And since mass loss is small, this is one other thing that we were worried, that if a lot of mass is being lost from the disk, then the spectra and the luminosity will go down. Spectra will become softer and the luminosity will go down from the Keplerian test. But what it turns out that the mass loss is not very significant. Okay, and it's few percent only. It's not going to affect the luminosity of the spectra much. Okay, thank you very much.
Thank you, Indranil, for a very nice presentation and timely finishing it. So this is the time for questions or comments. So please raise your hand, or maybe you can type the question in the chat window and I will read for you. Yes, Pankaj, please go ahead.
Can you hear me?
Yes, we can.
Yeah. Okay. Indranil, very nice presentation. So the one thing I have a couple of questions. I don't know. I mean, if I'm allowed, but I will try. So the very basic is like, so for this radiation-driven wind, you need to have a accretion disk which has to have a high luminosity, right, or efficiency.
Yeah. No, it's Keplerian disk. Yeah, Keplerian disk have high efficiency.
Yeah. So by Keplerian, you means standard Sakura signal, or it can be slightly, basically that one. Okay. Yeah. So, and the other thing is that you just showed that the m dot is like something like 3.5 or something 3. In what unit is it? It is not.
It's an Eddington unit, but if you calculate the luminosity, it's less than the Eddington luminosity. It never crosses the Eddington luminosity. It's I think 3.5 is around 0.2 or something Eddington luminosity.
Okay, so probably, so you have taken this eta factor into account that people usually take like 10% or something.
No, actually, I calculated from the expression of whatever Sakuratsune I have calculated for the flux.
Okay.
M dot by, I forgot the formula.
Yeah, that is okay. Okay, I understand, and I know that it can be looked into the literature, so yeah, that is okay. So the other is like you commented, I mean that microquasars often show the state transition.
Yes.
So how long the state transition lasts? I mean, in the terms of and how frequent is it? If you have any typical idea.
Yeah, typical. I'm giving you typical because
yeah, typical. I want typical because
so
you compare
whole thing for an outbursting source will be this whole cycle will take about 3 to 4 months, and it stays in the high soft state. Sometimes my arrow is sort of getting lost. So it stays in this high soft state the least. Okay, it's about 2-3 days. Okay, and then it starts to transit to this low soft state. Low hard state. Okay,
that is where the jet is, right?
Yeah. So this region, I have not explained everything. This region is called the quiescent state. Okay, so you don't really see the object very well at this state. Okay, so it takes about 2 to 3 days in this soft state, then another 2 to 3 days a week in the quiescent, and then after some time that you see it in the low hard state, and in the low hard state it stays the maximum.
Okay. So so
I can give you the numbers, but I'm forgetting what are the numbers for the how long it stays in the lower state.
Yeah, I asked this in the perspective that you raised the question that it seems that there is a connection between AGN and this one.
Yes.
So do you think that if, I mean, you particularly pointed out this low LLAGN, low luminosity AGNs, where you are, I mean, there has been a study or there are a study going on comparing the two.
Yes.
So, but I would like, why not other AGNs? The other thing is like, if you do a population synthesis study, let's say,
right,
so you expect to catch some sources which are, right, I mean, different phases of the population or the time sequence.
Right.
And then you at least expect to see the state transition in them.
I mean, you have to see, I mean, you will not see a state transition, but you will see an ensemble, right?
So, yeah, ensemble. So, I mean, at least you should expect that there should be, if there is
there. It is there. I mean, there are, I have to look into the literature. I can immediately think about who was it. It was, it is a Southampton group. Okay, so they.
Okay. So McHardy group
probably published 2-3 papers.
Okay.
Where the LLAGN, the low luminosity agents, with the low hard state, and they have. So you understand that these are very difficult studies. I mean, it's
yeah, I understand. That's why I'm asking, because there is two different questions here. So,
but they have. I'll look into the literature. I read few papers where they are suggesting that these particular agents will fit in the intermediate state. I mean, so this something like in this state, and some of them will fit in this state. So they have given some, some papers are there.
And okay, so if it is that one, so I'll just ask a connected question. So when you say that there is a state transition, does it mean only spectral state transition or flux as well as spectral? I mean,
flux as well as spectral.
Okay, fine. And now coming back to the simulation, my last question probably, sorry. So you said that there is a outflow boundary all along except the downward side, I mean where the accretion disk is residing. The plane.
Yeah, this one, right? Yeah.
Yeah. So, and you said that okay. Yeah. Okay, I thought that probably it is the sink only as a whole along the
Keplerian disk. Basically, it's
this black hole. Yeah. Okay.
Matter falling in. But the point is the The resolution we have taken, this sync has no meaning. I mean, it's just.
Yeah, it's just probably within one domain or two domain. I don't know much.
It's less than a one domain. It is gone.
Yeah, so it just okay. So it has. So, okay, sorry, I forgot one more question. So in the soft and hard state example that you showed, there is a disk dominant there.
Yes.
It seems that even the location of that disk component shifts during this soft and the hard state. I mean, I don't know if it is general or it just particular example, so I caught it up. So I mean,
could you repeat the question now again?
So in the left plot, this component is peaking around somewhere around 0.2 keV or something like that. In the right one, it peaks around 2 keV. I mean, it's like
yes.
quite significant change.
Yes.
So is it a generic one or
generic one? Because what you assume, or not assume, I mean, what you can argue is that when, so let me just go to this, maybe this one, okay? So when it is a low hard state, okay? So let's say the bottom figure, okay?
Yeah.
The Keplerian disk does not come very close to the central object, okay? So the temperature which will produce that bump is lower. So it will peak at a lower temperature, and therefore the peak frequency will be lower, okay? And if it comes up to the ISCO, then you know that it maximizes at around, the flux maximizes at around 4 Schwarzschild radius. And that is around 1 keV or 2 keV, depending on the central mass.
Yeah, central mass, yes, agree.
Okay, so therefore, say Cygnus X, sorry. Anyway, Cygnus X1, this is Cygnus X1, right? Cygnus X1, the central object, I think, is around 14 solar mass.
I don't know. I think it's around 10. Yeah, I mean, it's okay. It's a similar order, I think.
I think around 14, as far as I remember.
Yeah.
So if you calculate the ISCO and find out what is the, I mean, what should be the 4RG and correspondingly what should be its temperature, it will come around here.
Okay. And in the simulation on the axis, there were many.
Pankaj.
The last one, sorry.
Yeah.
It's a technical one, so I'm just asking because on the in the axis where, I mean, people usually see jets, there are sometimes even downward motion of the fluid.
There is
sometimes there is the arrow is downward flowing something
here.
I can see downward flow, but I'm not sure. I mean, if I can.
Yeah, there. It depends on at what state, but it is there. There is a slight downward flow. Yes, it's there. Around here.
Okay. I will probably talk later.
Okay.
Okay. Yeah. Thank you.
Thanks, Pankaj. So the next question by Varun. Varun, please go ahead.
Hi, Indranil. Thank you for your talk. I wanted to ask whether these failed winds can also be observed. Or
I don't know. I mean, whether these failed jets can be observed. What should be? One has to work on it. So, what should be the observable that can quantify as a failed wind? Because these are all density plots, right? So this is density and these vectors are the velocity vectors. So when it fails, how does it affect the radiation? Because when we say we see, we actually see the radiation, right?
Correct.
So one has to work on this. I'm not very sure what should be the observable.
Okay.
The good
and
question.
Then one thing you mentioned is.
I did not think about it.
And one thing you mentioned is that that the micro quasars do sometimes harbor neutron star also as a compact object. So,
it has been seen. I deliberately sort of did not discuss the neutron star case, but this general picture, where is it? This general picture is seen for accreting neutron stars. Okay. That you see in the soft state, corresponding soft state of a neutron star, you see a wind, while those neutron stars which have jets, they show the jets in the corresponding hard state. It is slightly different from the hard state. It's a bit different from a black hole hard state or a soft state. In this talk, I deliberately did not, because I am sort of all the time comparing microquasar with the AGN, and since both for AGN you should have a black hole, so I kept the comparison with two cases where we both have black holes.
But there are quantitative difference between neutron star in microquasars in terms of spectral as well as in the outflow winds.
I can suggest few papers which discusses this, that this similarity, this general picture.
Okay. I'll ask you. Yeah. Thank you.
Are there any other questions or comments? If not, so let's thank Indranil once again for a very nice presentation. And we hope to see all of you in the next seminar, which will be next week, next Tuesday on regular timing. So see you again, everyone. Bye-bye. Stay safe. Thank you.
Bye. Thank you for listening.